Hello everyone, welcome to part 2 of topic 7, where we discuss machine learning techniques. And in the previous part we introduced some concepts of machine learning, and we mentioned also there that data should be large enough to represent the system or behavior that we are interested in. So the quality of data is also very important. So it is not only the size of data, but also the quality of data. For example, if you have large data, but it's highly correlated, then as we mentioned also previous part, that it might not helpful. And okay, what is the meaning of quality of data? The data should carry information. So maybe the information is hidden there, so might not be visible directly from data, but we need machine learning to extract information. But there should be enough information to capture the behavior of the system. There is a general rule that for machine learning and in data science in general, that garbage in is garbage out. So if we have a machine learning, but we represent the data that we we are interested to model it, but most of data, or 95% of data, was biased, noise, junk data. So when we apply them to machine learning, of course, the model will be also garbage. So the model is not representing what we are looking for. So it is important, the quality of data. We should ensure the quality of data sets. So low quality means that the data that we have that don't represent the real problem, or maybe we have missing a critical part of data, so critical part of attributes that they are not there. Also, unbalanced data can be one reason for low quality. For example, if we are interested to check certain or to make some classification, that is it a faulty motor or healthy motor, and we have, let's say, 10,000 input data for attributes, but out of this 10,000 we have 9,500 for healthy data, and we have only 500 set for the faulty data. So when we make if we make the learning based on all these 10,000 data as it is unbalanced. So our machine learning will tend or will bias toward healthy output. Okay, so we need also to have some balancing data. Of course, if data that we have is already unbalanced, there are some techniques that how to handle this problem. Okay, so we have actually several sources of low quality, or several reasons makes the data low quality. Like, for example, highly linearly related or correlated data, redundant data. All these things are reducing the quality of data, and also can be source of some errors in the machine learning computation. Because in machine learning computation, some algorithms that we need to have, for example, inverse for a matrix. So when the matrix is highly correlated, then we might have a high condition number, and this makes the matrix is known as ill-conditioned, and then we will have very large error in the computations. So several reasons that we need to check the quality of data set. Okay. So sometimes data can be hidden, or some attributes are hidden. Let us see or look to this example. So now assume that we have this relation. Of course, now I am giving mathematical relations, but as I said, that usually machine learning, we are not interested to apply machine learning when we have deterministic relation. Okay, because we can deal with them with math. So machine learning, that when we don't know any mathematical mapping between input and output, or the math that we have, or the mathematical equation that we have is very low accuracy. It has very low accuracy due to noise and other inputs that might be missing. So anyhow, let us take this simple example that y equal to x1 plus x1 times x2 minus 10x1 square times sine by x3. So this is the relation between y, the output that we are interested in, and the inputs. And this relation that we don't know it, and we like to represent them by using machine learning, or to extract the mapping using machine learning algorithm. But look to this equation now. x3 here, we have 2. But if you look here, 2 times pi, this will be 0. Here, x3 equal to 3. Sine 3 pi equal to 0. 5 pi equal to 0. 0 sine 0 is 0. Sine pi is 0. So what that mean? It means that x3 will not be represented anywhere in the output. So it is missing from the output. So x3 is missing now due to this equation. Okay. Sometimes that we don't know even the attribute. Sometimes we don't know this attribute, which might affect also the output. Now, when we make machine learning algorithm that we want to have the relation between y and x1, x2, x3, that it might give very large errors if x3 is not integer number like this one. Okay, so you can see here, for example, for if we have in the testing, if we have x1 1, x2 1, x3 0.5, so it is not integer number. So what happened now? The model that we have, that we constructed, gives us 2, but the actual gives us -8. In this case, actually the difference is very large. So the model gives us -8, the actual gives us -137. So you can see it is very big difference, and we can say that this like machine learning model is garbage. Why? It is not useful for any x3. It will be useful only if x3 is an integer number. Okay, this is a very simple example. As I said, that the attributes might be also missing. Might be also like missing attributes, or we don't know about this attribute. If I just give simple example from health system. So if we have, for example, if we like to see those are smokers, that the people that they smoking, and they got some kind of lung disease over many years of getting this smoking. And then we might have this machine or this database that we have millions of people around the world. Of course, it is very bad to habit to smoke, but it's still people that are smoking. And then we have, for example, age of person when he or she starts smoke, and then number of, for example, cigarette per day. Maybe the body mass index, maybe the blood pressure, if they have some pressure in blood pressure, or if they are diabetic or not, and blah blah blah. So we have a lot of data that we have. Then we have here the disease obtained after, let's say, after 20 years of smoking. Okay, so you can see here in this table that people, they got disease. For example, this one got for example like chronic infection. This guy got cancer, this guy healthy, this guy healthy, and this guy gets something. So now when we build machine learning algorithm of this based on this health like database, we can build some machine learning algorithm that if we input some new case, that case was not shown before, that what do you think that after 20 years this guy will get some kind of these diseases, then they might give us some result which can be, for example 60% accurate. So why 60% accurate even we use all these possible data that we have? Because one reason, or one expected reason, that because we have some missing information that it is not easy to find, or sometimes even we don't think about. One reason may be related to deep in genes, genetics, for example, the order of some people, or maybe the habit of eating, or maybe it can be actually any reason. So in this case, we have even we collected a lot of data, but it might be always difficult to have very high accuracy. So we can find some people, for example, they are maybe 90 years old and they are smoking for 50 years or 60 years without problems. And we can, at the same time, we find people that only 40 years old and they are smoking for 10 years and they got cancer. So how can we differentiate between what is the real reason about that? What is the deep reason for that? There are actually many questions like that. Not so, we don't have like final answer yet. We have some like expectations, or we can estimate what are the reasons, but as far as or as much possible data that we can obtain, then we should use in machine learning. Okay. Yes. Here we have another example, and this example is related to cars, for example, second order car, and we like to build some machine learning in order to estimate the price of your car that you want to sell. And in that case, you can go to some like websites that they sell used car or second-hand car, and you know that in every country we have such kind of websites. Here in Finland we have nettiauto.fi, so you can go there and then you can find the prices of cars, and then it depends, for example, the prices that the brand, for example, Toyota, Volvo, Mercedes, and so on. Then the model itself, the year of manufacturing, fuel type, is it diesel, benzene, or electrical car, then the color, the gearbox, is it manual or automatic, the status of the car, general shape of the car, is it very good or excellent or not bad, or and so on. So, and then we find that this car was sold at a price of 16,000 euro, for example, and it was there in the system 7 weeks before it sold. So this is the waiting time of the car. We have another car, for example, and it was sold at 39,000 euro, but it stayed in the system 15 weeks, and so on. So you can collect all this data, and then you try to build some like model or some machine learning model to express or to learn how to estimate your car or other cars. Of course, what kind, those are, we call them attributes or factors that we have from x1 up to xm. As much attributes you get, which can be related, of course, we should use. And here is the outputs. So the outputs with that, the sold price, and also we assumed here the duration to sell is also an output. Because sometimes if you have a certain car and you or maybe you have an agency, for example, that you sell used cars, and then someone came to you and he wants you to sell his car or her car, then you ask what is the duration time that that you can wait. For example, if they told you that I want to sell my car today, then of course the price can go down. If they said that I don't care about the time, so I like to have the maximum price, then the price will go up, and so on. Okay, now if we want to build this relation or the machine learning algorithm to capture this relation, the machine learning, it can have different forms. For example, this is the most like the simplest and also most well-known regression model is a linear one. So the linear regression is very well known, and it is very like simple to find the values, and also the solution is usually unique. So we have a global solution for this kind of models. So we have here, this is the output. This is yi can be the output 1 or output 2, depends. This is the y1 is the sold price, and y2 is the number of waiting weeks, estimated, of course. All these are estimating. And then t here is the number in the data. So we have here, for example, we have maybe here number 1, number 2, number 3, number 4, number 5, and so on. Okay, so we have now this relation, and this a are the parameters that we like to find. So these are, we are looking for these parameters which will optimize the result. What do I mean? What we mean by optimization, optimizing the result means that the output of this equation will be very close to the output of the database that we have. Okay, and then we have, this is the model error that we don't have anything to do with it. So this is the usually it is Gaussian noise, zero mean usually, and this is what we have. This is the model error. You cannot do anything with that. Of course, you can reduce it sometimes if the relation is not linear between these inputs or factors and the output. Then if you change from linear equation to nonlinear equation, this noise or this error can go down. Otherwise, it is always there. It is always there. It is the representing the uncertainty part of this model. Okay, now you can see here that this parameter is also, if we have optimized factors or optimized attributes, it means that if we make those attributes, all these attributes, for example, from 0 to 1, for example, or from -1 to 1, or from 0 to 2, or from -2 to 2, or from whatever. So, but they are all of them, they are normalized. So if these parameters are normalized, then these factors that we are looking for will represent the importance, okay, of this factor in the price. Okay, for example, assume that this x1 representing the fuel type, for example. Is it diesel or benzene or electrical or gas, for example? Of course, now we need to convert this from symbolic representation to math, to numbers. Okay, to represent them to numbers, maybe you can define. You can define, for example, for diesel, I will put +1. For benzene, I will put, for example, a +0.5 or +2. And for E, I will put, for example, -1. And for gas, -2. You can put some numbers or making some quantification for these like descriptive inputs. Okay, and then this A, if A is very large, okay, then it makes that this factor is very important for the price. For example, assume this x2 is for the gearbox type, so it is like automatic or manual, and in this case A2i was very small number. What that mean? It means that the impact of the car to be manual or automatic has a small effect on the sold price of this second-hand car. It might have like large price in the new car, but in the sold in the second-hand car might not have that big price like the fuel type, for example, and so on. So this is the very general representation and explanation for this equation. And then we have, of course, many simple techniques in order to find what is the optimum A1, A2, A3 up to AM. And once we find them, then we can check, we can make the validation if this model is good or not, because we have already the database that we have, as I mentioned. Assume that you have 10,000 car here, so you can make, for example, the learning over, let's say, 5,000 car, for example, and then you can use the other 5,000 for testing or for validation to check that your algorithm is working fine or not. If you find your algorithm is working fine and it is very nice, and the error, for example, let's say plus minus maybe 15%, so you can rely on this model, and after that you can start using it in your applications. Of course, before you start using it, you need to make or to repeat the learning with all data set that you have. So first we check that the model is good, the linear model is working fine, it can estimate the parameters very well. Then after that you can apply it. And you need of course to remember that you have to be balanced between the cars. For example, if you use 5,000 in your learning, it shouldn't be that for example 4,500 car for one brand, and the other 500 for 20 brand, because in this case we will have unbalanced learning, and then we will have large errors. Even if you make the testing or the validation with the same brand that you use here for 1,500, it might give you good result, but still it is not good if someone bring to you some new brand or different brand. Yes. If when you build the model, either linear model that we show on before or maybe non-linear model, so you use non-linear model, and you find that during the validation the result was not good, or your algorithm was not able to capture the relation between the attributes and the output. What are the reasons for that? So what you think about the reasons? So we might have different reasons. For example, the actual relation is not linear. Then you need to think about non-linear model, and we will see some trick to how to represent non-linear models as linear one. This is what we are going to show later. And there are missing important features from data, so there might be some missing information there. Maybe the type of if the car has electrical seat or not, or it is leather seat or not. So there might be some other important information can affect the prices of the car, and data size is not enough to capture the relation. This is one reason. The data quality is very bad, so it can be bad data. For example, biased data. So because you are collecting data from some general website, so maybe there are some people for some reason they bought wrong data. Okay, they bought, for example, that they sold this car. Actually, they didn't sell the car, but they marked there that they sold their car with that cost, and it was not true. So this, of course, making biasing in your data that you use for learning. Okay, now we end we complete with the regression. So now we talk about classification, a little bit about classification. So we don't have a numeric output, but we have classes. For example, we have two classes like dangerous situation or safe situation, spam, email or not, faulty device or good. For example, this is used in quality control. Generally, any hypothesis A or B, or it can be more. So it is not necessary that we have only two classes, it can be any number of classes. For example, in fault allocation, if we have like smart grid, where we have different stages, like we have generations, we have renewable energy, then we have high voltage transmission, we have like medium voltage transmission, we have low voltage transmission, we have batteries, we have many things connected together in very complex scenario, and then we have some fault. So we can actually, for example, we are interested to allocate the fault. So we can divide this smart grid into zones. So we have zone A, zone B, zone C, D, E, F, J, and so on. So we might have like 20 or 30 zones in the system, and then we like to allocate in which zone that this fault has happened. So this can reduce the searching problem to find where is the fault. So now this is also classification. Even we have 30, we can have even more number. Also in like speech recognition, for example. Now when we talk, so we have many words that we say that, for example, we have 3,000 words that we speak with generally for the automatic system, and out of 3,000 words, then when we say some word, then the pattern recognition or the voice recognition system or the speech recognition, they try to make or allocate this word to one of 3,000 classes. So we have 3,000 words, then we want to have that. Sometimes we have statements, so we don't need to be aware about the word itself, but we want to have the statement that what with the meaning, what they want to know. For example, in this assistant, for example, in Siri or in Android, in Google, so you say that, for example, what is the temperature today? So the system, they want to know what you want instead of each word what it means specifically. Okay. So the classification learning is quite similar into the regression, but now instead of numbers, we will have like classes. Okay, so almost the same problem as with regression, we will have them in the classification as well. So now if we assume about, if we make survey about people, survey with people, like thousands of people that we asked them about certain cars, and I want them to like mark if this car is expensive, the price, or fair, or cheap. Okay, and then we make, for example, we can have any number of attributes, but let us take only 2 attributes from the database to make it visual for you. Then I take only the price and the year of manufacturing of this car. Okay, so now we, for example, for certain type of certain brand, I mean, for example, Toyota, then we ask them with the price and the year of manufacturing. So maybe certain type, certain brand, and so on. So now people start to mark. They have this. Maybe they can do it like automatically over their mobile phone. Then we start to collect information. So this guy, for example, see this car that it is very old and this is the price, but they can see that it is a cheap car. Some others for the same car, they can see it fair, but for someone that like newer car, so but the same price, they can see that it is expensive even it is a newer car, and so on. So people are thinking differently. They have their own way of evaluating the prices, their own experience. So we collect such kind of data. So we have between like expensive, cheap, and fair prices. Now, based on this information that we collect from the survey, we like to build some automatic machine learning that it extracts the way of people, how they are thinking to estimate the prices. So to say that if this car is cheap or fair, or so if you ask this machine learning or this intelligent agent, you ask them that what you think about this car with this price and with this year of manufacturing, then they can tell you that, oh, it is cheap car, so you have to go for it, or it is expensive, avoid it, and so on. Okay, so it gives some advices. Now we have this kind of classification. The classification type is, it can be, for example, linearly separable, like this one. So we can easily separate between these 2 kind of information or of classes. For example, cheap and expensive, dangerous or safe, spam or not spam. So and those are the attributes. Here we assume also we have 2 attributes, x1 and x2. Then we can divide this with a linear class. So it is very simple actually to learn this or to teach this to machine learning, because all what you need to know actually is having this line. So you can build this line based on x1 and x2. So it can be, for example, a1 x1 plus a2 x2 plus for example, A0. So we have this relation now. And now if you give new x1 new and x2 new that it was not in the data here, you give it to the system. So if it is greater than 0, then you will classify it as star. If it is less than 0, then you will classify it as circle. So it is very simple to be in this way. But unfortunately, it is almost in reality or in practice, we don't have such kind of nice linear separable problems. Because of noise, actually, even if the problem itself was linearly separable, even if this happened, but because of noise, because of bias, so then you can have, for example, star here or something like that, as we can see. The second kind of types of classified data is nonlinear data. So in the nonlinear that we have, as you can see, so we have class here, so we have it here. So actually there is no linear line that it can separate between these classes. So what we need here to do, we have to have some kind of nonlinear classification. So we can say that if the new input x1 and x2 new data that you have, if it becomes inside the one of these circles, then you classify them as a star. If they are outside, you can classify them as circle. But it is not easy actually to implement. It is not easy to optimize such kind of when the data is distributed in this way. Okay, it can be even like more more nonlinear or highly nonlinear with noise and like biased data. So you can see that the data can be like interfere to each other in this way. So it is very hard to find some like nonlinear map to collect all these and will not explain this one. So it is not possible. So this is one problem that we have with the classification when it is highly nonlinear. Is there a solution for that? Fortunately, yes, there is a solution for that. So we use what is known as linear trick, actually. The linear trick that we use to convert nonlinear to linear form, and it is widely used in some famous classification techniques like support vector machines, and I'm not going to explain it in this introductory lecture, but as I mentioned before, we have our course machine learning where we take the concept and the mathematical concept in details about the support vector machines. But just to give you a simple idea or very fast introduction about support vector machine, usually actually if you want to separate between any data, usually we look to the data which is very close to the border. So because this one actually will not affect the shape of this line. What is the affecting the shape? What is the affecting this A1 and A2 and A0? Actually, these data, which are, we call them support vectors. Those data which are very close to the border. But this one, these are not actually affecting those at all, because they will not have direct impact or direct influence on the shape of this line. The same actually for here also. So the shape here depends on the data which are close to the boundary from both sides. This data, for example, this one and this one. This is generally what is the meaning of support vector machine. But the linear trick here that we can convert from some systems are in some space they are nonlinear, but we transfer them to another space, larger space, which can be linear. I'm not going to the details of that, but I will take very or extremely simple example, or maybe the simplest example that they can explain. It can explain this concept. Assume that we have only one attribute x, not two attributes, and the data was classified in this way. So we have here the circle, which means that, for example, it is faulty. This is the attribute. Sorry. So the attribute here means that, for example, let us assume that it is the maybe temperature, okay, temperature, or it can be for example vibration, or it can be anything that, but we have one measurement here, okay, and we have two classes. Okay, now if x is less than certain value, it means that the system is like faulty, the temperature is faulty, or the system is faulty. If it is larger than some value, it is faulty again. But if in between, then it is healthy. The system is healthy. So now we like to build linear relation. Of course, you can have circle here, but we are interested to have a linear relation to classify this. There are many reasons that why we prefer linear relations. One of them is the linear equation is usually convex, and when it is convex means that we have a global minimum or optimum solution that it can be easily find. So and there are many other reasons, and sorry. Because of that, we are interested to build it with a linear. But it is apparently here that we cannot linearize, or we cannot use linear line here. If you put that line here, it is not working. If you put it here, it's not working. So it is not working. You cannot separate them with line. One possible way that we convert from one dimension to two dimensions. So it is one, we put it as x, and the second dimension, we put it x square. As you can see, so we have x here and x square. Okay, now assume that this is 1, 2, minus 1, minus 2, minus 3, and this is 1, 2, 3, and this is in between, so it can be 0.5, 0, minus 0.5, sorry, 0, and 0.5. Now, when you take square, this will be minus 2 square is 4, minus 1 square is 1, minus 2 square is 4, minus 3 square is 9, and so on. And that's what the result that we will have. Now it is very easy to use linear line to separate these two classes. So now we transfer from one dimension into two dimension. The same concept is applied even for higher dimensions. So sometimes we have, let's say, like 5 attributes, but the relation is nonlinear between 5 attributes, x1, x2, x3, until x5, and then by using some trick of, it is called kernel, so we use some trick that we convert from 5 attributes, let's say, to 30 attributes, or to 50 attributes, or to 20 attributes, and we can find that in that new space, because now we have new space. In that new space, the data is linearly separable, or can be closely to be linearly separable. Okay, so it is different topic about how to find the optimum kernels for such kind of problems. A neural network. Okay, let us keep this for the part 3 in this course. So next part we will talk about a neural network, and next part will be also the last part in this topic. Thank you very much.